Okay, so welcome everyone to the ILLIXR Consortium open meetings. Delighted to have you all back. Today, it's a pleasure to introduce Mihai, who is Mihai Bujanca, who's a research assistant at the University of Manchester, and he's been working on Slumbench. And I think almost everybody here, I assume, know about this work. It's been pretty influential in getting together a lot of the SLAM technology visible to systems people. So we're really excited about the possibility of integrating Sunbench and ILLIXR, and Mihai is going to start the conversation.
Yeah, thank you very much. And
and I should say, Mihai, sorry, I should also introduce Mikhail Luhan, who is the lead on this work, and we're really delighted to have him here along with who's that? Hi. Okay, cool. All right, we'll get started.
Okay. So thank you so much for the invitation, and it's a pleasure to be here. And I think ILLIXR is really exciting and a really cool way of driving things forward. So I'm Mihai. I'm a research assistant at the University of Manchester, as mentioned. I'm going to be talking about Soundbench, which is a performance, accuracy, and robustness evaluation framework for SLAM systems. The source code is publicly available, and you can access it either via the QR code or the URL on the bottom left. So just to contextualize things a little bit, I think you've all seen this diagram. I'm going to talk a little bit about how I think that Slumbench fits into ILLIXR. So in principle, I think Sunbench addresses some really important aspects of the perception pipeline, including integrating a variety of sensors such as cameras, IMU, LiDAR, event cameras, a lot of other sensors, visual inertial odometry, and scene reconstruction. And so we not only are able to benchmark these various aspects, but also provide out-of-the-box working algorithms. So more specifically, the aim of Sunbench is to automate reproducibility of an evaluation of SLAM and spatial AI systems. And in order to do this, we've designed a framework that is algorithm agnostic, dataset agnostic, and context agnostic. So what we mean by this is that the framework itself is not tied to any specific details of algorithms, datasets, or running platforms. But we do bring together a variety of algorithms and datasets, and we are able to run experiments across different computing platforms. Here I've mentioned Spatial AI. This is something that I'll be coming back to, and is going to be quite important to our vision of Sunbench and progress in the SLAM community. So at the moment, we have a host of different supported algorithms, and we've tried to keep up with the progress. So you can see that we have algorithms spanning from really early SLAM algorithms such as PTAM to the latest algorithms such as OrbSLAM, which was published in 2020. And all of these are accessible through the repository and can easily be built and tested on a variety of data sets. In terms of data sets, these are the data sets that are on the main repository. We have a couple of others that are on the development repository, and hopefully soon those are going to be updated to the main repository as well. So back to the notion of spatial AI. This was introduced by Andrew Davison in a paper called Future Mapping a couple of years ago. And the way he put it is that the goal of spatial AI is not abstract scene understanding but to continuously capture the right information and to build the right representation to enable real-time interpretation and action. There are some excellent talks available on YouTube, but to summarize, the basic idea is that SLAM has evolved beyond its initial formulation. And now the term spatial AI can be used to describe these extensions of SLAM to more complex representations. And the way we think about spatial AI is in 4 levels. So the bottom level, level 1, would be camera localization. This is a system simply being able to answer, where am I? It doesn't know anything about its surroundings, about the meaning of its surroundings. It can just answer, where am I? What is the location of the camera? Level 2 is reconstruction. So beyond just saying, where am I can also say something about my surroundings. I can also say something about what things look like around me, but I don't have any understanding of what they mean. Level 3 is scene understanding. So here, each bit of geometry, the things that are around me now have labels, now have classes assigned to them as to this part of the scene being a chair and this part of the scene being a human, and so on. And then level 4 would be interaction understanding, where we're trying to understand how different parts of the scene, and usually agents and parts of the scene, interact. And I hope you can already see the relevance of these levels to ILLIXR. And I think ILLIXR is a step towards encompassing all of these levels and getting to interaction understanding. So I believe level 4 is perhaps one of the end goals. Now, given this view of SLAM evolving into spatial AI, you notice that besides the fact that there's a multitude of tasks involved in spatial AI, there are other features that add complexity. So spatial AI systems may be using different types of sensors. So these could be cameras, could be IMUs, they could be LiDARs, or other types of sensors. They often run on a vast variety of computing platforms, ranging from cloud computing and powerful desktops to mobile phones. And then the environments that algorithms are expected to run in are also very diverse, and they vary in their structure and the content. And depending on the specific application and the specifics of the environment that you are going to use a spatial AI system in, you're going to need different kinds of features. So in order to help with this in Soundbench, we've put together a variety of algorithms, so ranging from traditional SLAM to having depth estimation, semantic understanding, and then also being able to reconstruct non-rigid objects. So these are moving objects such as humans or clothing. Having data sets that cover all of these aspects, so semantics, moving objects, the classic RGBD and stereo. Having metrics to assess each of these levels, and then being able to run across a wide variety of architectures. There's a question of what are the properties of SLAM systems. So we've identified 4 characteristics that we want to assess using our framework. One of them is accuracy. So for each of the various tasks, we want to understand how close to reality, how close to the ground truth does a system perform. Complexity of representation. This is essentially what level of spatial AI does a system achieve. Efficiency. So what are the resources needed to accomplish a certain task? And then robustness, being able to perform well even when things go wrong. So we're going to go through a little bit of the history of Sunbench, and starting from the lowest level, from level 1 with camera localization. So the first version of Sunbench was introduced within the Pamela project. This was this was a paper that was led by Luigi. So the Pamela project was a consortium of 3 universities, Manchester, Edinburgh, and Imperial College London. And the initial question was just, how can we understand SLAM systems? And what they did was take one SLAM system, this was Connect Fusion, and try to understand all of the details, like have some really thorough evaluation of all of the parts going into the system. As I mentioned, this was only pose estimation, so just looking at level 1. So what they did was have multiple implementations of Connect Fusion, which initially did not have consistent outputs. So the CUDA version and the C++ version perhaps were not always yielding the same outputs. In trying to understand why, they've created the ICL Nguyen dataset, which is still widely used, which is a synthetic dataset with pose and 3D model ground truth. And using these 4 implementations of Connect Fusion, they assess 3 metrics: so the speed, the power, and the accuracy of the SLAM systems in pose estimation here. Moving on to level 2, we wanted to evaluate to be able to evaluate the quality of the reconstruction as well as the pose estimation. So Sunbench 2 introduced head-to-head and multi-objective benchmarking. So by head-to-head, we mean that we were able to directly compare different SLAM systems, and multi-objective, meaning that we were able to assess both the accuracy and the efficiency of SLAM systems. So taking the lessons from the first Sunbench version, a framework was designed that was able to bring together a multitude of data sets and algorithms and metrics and perform this head-to-head benchmarking. Now, today's version is largely based on the work done in Sunbench 2.0. And in order to be able to do this, essentially the lessons from the first version of Sunbench were that there are many parts of that most SLAM systems have common methods, and they were broken down into 6 methods. So there's a configuration step where all the hyperparameters are being configured, command line instructions, and so on. Usually some systems have some sort of initialization routine. Then there's a processing phase, which runs in a loop where new inputs are being read, they get processed, and then outputs are being sent back to the evaluation framework. So outputs would be things such as the camera pose, and finally, just any cleanup that is necessary for that particular SLAM system. So here we have a video, which I hope will run. I've been having some trouble with the network. Okay, so here what you can see, maybe I can loop this. Okay, this is OrbSum2 running on one of the data sets that was introduced in Sunbench 2, and what you're seeing is at the top there's the inputs, and then in the mainframe you get a very sparse map being constructed by OrbSlam. So these are just features being tracked in 3D. And at times you can also see the pose that is estimated. And so as part of Sunbench 2, there are also routines to transform the logs that are generated into nice plots that can be used. They're pretty much paper ready. So you can see a violin plot that has been generated from the evaluation output. Moving on to level 3.
So in the Slumbench, so what kind of so these are the main the accuracy metrics are ATE and
so in this case we're just showing ATE, but by this point already we have reconstruction error, AT, and relative pose error as well. In Sunbench 3, which I'll talk about, we've introduced new metrics as well.
Right. Okay. Yeah.
So moving on to level 3, in Sunbench 3, in a work that was jointly led by Paul Gafton and myself, we recognized that systems were getting increasingly diverse and complex. And so this was a paper moving to evaluation for level 3 and also sort of thinking towards level 4. So this included 3 categories: dynamic reconstruction. So again, being able to reconstruct moving objects such as humans, clothing, curtains; semantic reconstruction, and then we also added in depth estimation. Depth estimation was added because we recognized that pretty much, phones have cameras, pretty much all devices have cameras nowadays. Even though they don't have depth cameras, there has been a lot of research coming into doing monocular depth prediction. And so we believe that this is something that can be really helpful with SLAM when direct depth readings are not available. So here I'll have 2 samples. This is semantic reconstruction being done within Sunbench. So here you can see that the objects being labeled by, I believe this is semantic fusion running within Sunbench. Of course, here we've added metrics as well for being able to evaluate the quality of the semantic reconstruction. So these are both in 2 dimensions, that is how well the semantics are being inferred at the frame level, and then also in the 3D map, how well the semantic map is being reconstructed. Should I perhaps restart this? I appreciate that it's been sort of stopping and starting a little bit.
Sure, if that will help, yeah.
So what's happening is that the system that is running computes for each frame a semantic segmentation of the frame, and then that data is being projected onto the geometry. And at the end, you get a map of the environment where the geometry is labeled with the semantic classes.
And you're doing the reconstruction also as part of this computation.
Yes, but this is an external system that is integrated into Sunbench. And what Sunbench has added is the capacity to evaluate the various aspects of the system.
Yeah.
And similarly for dynamic reconstruction, this is dynamic fusion running. So this is a data set where there are multiple cases with non-rigidly moving objects, and we're trying to assess the quality of the 3D reconstruction. So in this case, what we do for this is that there is I believe the dataset has ground truth taken with a superior sensor every 100 frames or so. And we are evaluating the quality of the reconstruction of the system against that ground truth data. Okay, so far we've mainly been discussing accuracy, complexity, and efficiency of sound systems. Moving on, we're going to be talking about robustness to perturbation. So this was a recent paper called Robust Sound Systems, Are We There Yet? So by robustness, what we mean is the capacity of a system to perform correctly, even in the presence of perturbations. And by perturbations, we mean anything that might cause a system to fail. So in the GIF displaying, you can see a system that is not robust to dynamic objects. And so the map gets corrupted and the reconstruction essentially fails. So we've looked at several study cases. One of them is dynamic objects. So here we use the bond dynamic data set. Now, the reason that dynamic objects can throw off the reconstruction and the pose estimation is that a lot of the systems make the assumption that any changes in data will be due only to the camera movement. And under this assumption, it tries to compute the best pose that would explain the data from outside. Now, if the data from outside is not due to the camera movement, but to the other factors, this will have an impact and often cause a failure. Illumination changes. So here we've used the ETH illumination dataset. This is because lots of systems, but in particular, a class of systems called direct methods makes an implicit assumption that illumination will be constant. And so when that doesn't happen, certain systems end up failing. We're looking at fast motion. So this is the Europe MAV dataset where there are several sequences on a drone. And sometimes the drone is moving fast enough that it produces motion blur. Whenever there is motion blur, it becomes really hard to detect consistent features or lines or anything that could help with estimating the camera pose. And we've looked at these perturbations both separately, so with each of the data sets that I've discussed, and also together. So if you notice in the bottom right corner, firstly, there's a person that moves in front of the camera, but after the person comes out of the camera view, there's an exposure correction. And so this affects the perceived illumination of the camera. So what we're noticing here is that we need to evaluate these perturbations both separately to get an idea of how well each system performs under that particular perturbation, but that there is a sort of non-linearity in these perturbations adding up, and that, let's say, a dynamically moving object can affect the perception of the illumination as far as the system is concerned. So, have a couple more videos. Here we're looking at four different systems running on the bone dynamic dataset. The baseline in red is refusion. So refusion is a system that produces a 3D reconstruction and was published along with the bone dynamic dataset. So this is what we consider the baseline. refusion is designed to explicitly deal with dynamic objects. In the top left quadrant, we're comparing full fusion with refusion. Full fusion is our own system, and I'll be talking a little bit more about that later. Full fusion, through a different methodology than refusion, is trying to filter out any dynamic objects. On the top left, there is elastic fusion compared to refusion. So elastic fusion is a 3D reconstruction system that does not have the capacity to deal with dynamic objects. And you can see that elastic fusion, the reconstruction here fails. And on the bottom right, you can see a comparison of ORB-SLAM3 and refusion. So ORB-SLAM3 is a sparse system, a system that doesn't do a full 3D reconstruction, but only tracks the camera position. I forgot to say that the purple trajectory is the ground truth. So what the systems are doing is trying to be as close as possible to the purple trajectory. We're also highlighting that whenever dynamic objects enter or exit the scene, that there's a visible change in the quality of the pose estimation. So I think if you look at the bottom right, in a second, you'll find that now that the dynamic object enters, the ORB-SLAM3 estimation will start to fail.
So are you realigning the trajectories with ground truth as you get new poses?
Yes, we are.
Okay.
In some cases, that can, it does not affect our final readings of the pose quality, but just when you look at it, occasionally you have problems with things not the trajectory not being correctly aligned, and so sometimes this qualitative view of the pose estimation can be misleading, but most of the time it works pretty well.
Yeah, it's interesting to see how the trajectories just rotate.
Yes.
And they align. Yeah, it's pretty interesting. Is full fusion open source?
Not yet. We intend to make it open source.
Cool.
So what are the sensors you're using here?
So it generally depends on the algorithm.
No, for full fusion, I meant.
Full fusion, depth and RGB.
Okay. And then you have some performance numbers also in terms of compute time and so on.
So this version of full fusion was not designed as much to be to perform really well or really efficiently, as much as to bring together
Sure.
the possibility of, so you're not seeing it here. I'll show it a little bit later, but being able to do 3D reconstruction with dynamic objects and semantics. We have some limitations on that, such as the dynamic object always has to be in view if we want to reconstruct it properly. But I'll get to full fusion in a second as well. I just wanted to show another sequence where we're looking at illumination changes. So here we're comparing OrbSum2 with Elastic Fusion and refusion. And on this particular sequence, Elastic Fusion fails just immediately. Well, we're not entirely sure why, but the reconstruction is really poor. It fails pretty quickly. Refusion, which is the system I mentioned earlier, which is able to handle dynamic objects, is a direct method that does 3D reconstruction, but is quite sensitive to illumination changes. And I'll leave this video running a little bit more, but you're able to see in 2 instances when the illumination changes that refusion starts to lose accuracy. So here is one instance where, whoop, I'm sorry. So this is one instance where illumination will change, and you can see that it just went off quite a bit. And then it starts to recover a little, but there's sort of a failure to close the loop due to accumulated errors, and it goes completely off. The trajectory that it does really well is OrbSum2, which is, it's not sensitive to illumination changes, but at the same time, OrbSum is just a sparse system, whereas all the other systems here are also doing 3D reconstruction. So in spatial AI language, OrbSum is a level 1 system, and the other, whereas Elastic Fusion and refusion are level 2.
So you did you do extensive work with Infinitime at any point? We are curious about that. That's something we, yeah.
I've not, I wouldn't call it extensive work. We've done some evaluation with Infinitime. I remember it was really fast. It worked quite well on a lot of cases. Off the top of my head, I can't really speak too much of Infinitime, but I'd be happy to revisit it and have a look. I think it certainly wouldn't be wouldn't handle things like dynamics, but it shouldn't have any problems with illumination changes, because if I remember correctly, they don't use RGB data. I think it's just depth.
Yeah, we've been using it because of the speed, and there are some issues that we've had, but that's getting into the weeds. I was just wondering how much experience you all had.
So I've tested it a couple of times. I haven't done any real development on top of it. There is, within the newer version of Full Fusion, we were relying on Super 8, but yeah, I'm happy to talk about that.
Yeah, no, please continue. Yeah.
So overall, in terms of the qualitative results, we're kind of saying that Full Fusion does probably the best of the systems that we've assessed in terms of level. Well, Full Fusion is a level 3 system because it includes semantics, but in terms of dense systems, Full Fusion does best. For sparse systems, so level 1 spatial AI, OrbSum has proved to be really good and really robust. Still, I think the open loris data set, which is the data set where these perturbations are combined, is still quite difficult for any systems, regardless of whether they are level 1, 2, or 3. But it gets more and more challenging as you're trying to gather more data and understand scenes more. The qualitative assessment here is, based both on our interpretations of the numbers, but also the sort of the hands-on experience with each of these systems. So in this paper, what we've done was run the systems across 3 platforms. So we've had desktop, laptop, and an NVIDIA Jetson. And for the qualitative assessment, we've decided that we would also take into consideration things like whether it's easy to go from one platform to the other, to go cross-platform, or whether there are issues with things like, you can run it on one platform, but then you get segmentation faults or other issues in
So I'm curious about your baseline accuracy. I understand this is qualitative, but can you give us a sense for what is good versus very good? Like, how are you measuring for the dense landmarks?
Sure. So sorry. Well, so here we've in this particular paper, we were only looking at the quality of pose estimation. This is partly because I think only the Illumination one. No, actually, I think possibly the dynamic one as well had 3D reconstruction ground truth. But yes, here we were only looking at the quality of the pose estimation, not of the reconstruction. But that's a good point. That's something that we should be looking at more.
So did you see the, I mean, it may not be on the paper, but so we've seen like a dichotomy or not 100% consistency between the posed results and the final reconstruction. And so do you visually see the reconstructions, and would you, what would you say totally non-scientifically?
So based on my experience in general, I found that there's a high correlation between good pose estimation and good reconstruction. There are cases where this isn't, well, to be honest, how should I put it? If the pose estimation is bad, then the reconstruction is almost guaranteed to be bad.
Yeah.
If the pose reconstruction is good, then most of the time, I think with pretty much all the systems that we've tried, you get decent reconstruction. But I couldn't at the moment speak of exactly the numbers when I'm saying decent reconstruction. Just visually, it's pretty good.
Okay.
So just to talk a little bit about full fusion, the idea of full fusion is to do semantic reconstruction of dynamic scenes. So that is being able to integrate semantics, dynamic models, and the static background into a single framework. And part of the idea is that we can use the labels. So we consider a priori that having labels into the scene and being at level 3 is a desirable thing, but these labels can be used for other things, such as filtering objects that we know are going to be dynamic, such as humans, for instance. you asked earlier about the performance of full fusion. So in this version, which is the first version of full fusion, we haven't focused as much on getting it to be really performant. What we've done was used a modified backend of Kinect Fusion for the static reconstruction and a modified dynamic fusion for the dynamic reconstruction. And the reason we've picked these two particular systems is that they're pretty much, 3D reconstruction, or a lot of the 3D reconstruction work was based on the original Kinect Fusion paper. It's the same with dynamic fusion and dynamic reconstruction. And so what we wanted was mainly to have a baseline for assessing future systems and future versions. And this is okay. Seems like I'm having some trouble with loading the video. We can try to do it afterwards if you wish. So coming back to Slumbench, there are 6 functions as mentioned, and typically to integrate a new system, you only have to write about less than 500 lines. So I think for the same Kinect Fusion that's integrated in ILLIXR, it's about 300 lines. For more complicated systems that accept a wider variety of inputs like ORGSUM3, it's still less than 1,000 lines. So when you think about how much work you have to do to just couple one system with one new data set, I think there are real advantages in using Sunbench with systems in order to get access, firstly to all the data sets that are already integrated, but also to be able to do head-to-head benchmarking against previous work. And so coming back to how ILLIXR fits in, how Soundbench fits into ILLIXR, I think this collaboration would really benefit both groups. So on our side, the fact that we already have many algorithms and data sets that are integrated, and ILLIXR could benefit both from the evaluation tools, also the expertise that we've built over the years, and being able to integrate the data sets, the algorithms, and the evaluation tools within the broader pipeline. I think in the short term, for Sunbench, this could serve as grounds for being tested as part of a larger system. So far, we've mostly focused on either robotic systems or just sort of standalone SLAM, but I think extended reality brings some really exciting challenges, and being able to understand how well current systems work, and then how to build new and better systems that are able to cope with the demands of extended reality is very exciting, and it's also quite a challenge. In the longer term, the way I'm thinking about the collaboration between ILLIXR and Sunbench is that ILLIXR is really a huge step towards level 4, and sort of integrating all of the levels of spatial AI that we've talked about. And so I think with a collaboration, we could start thinking about building the basis for both for evaluation of spatial AI systems all the way to level 4, and also on exactly how to build the systems themselves. Yeah. So I'm really excited about starting a collaboration here. I think there's great benefit that we can have through this on both sides.
Yeah.
Just in closing, a couple of lessons from Soundbench, and I think with this and a couple of acknowledgements to our co-authors, there are a couple of lessons from Sunbench which could open a really good discussion. So dependency management has been difficult for us. What we started with and how we're currently still doing it is that we try to build one set of dependencies that are supposed to be working across all the systems. Now, the reason for this is, of course, that you would ideally want to have the various dependencies of the different SLAM systems set to the same version. So for instance, there are lots of different dependencies such as OpenCV, Eigen, G2O, a couple of others, which are very widely used in the SLAM community, and there are a lot of SLAM systems using them. Now, what you would like to ideally ensure is that any differences in performance are not due to using different versions of the dependencies, but that the differences are inherent in the SLAM systems themselves. And we've actually noticed when running OpenVINS and OrbSLAM, I believe this was OpenVINS and OrbSLAM, I think we've noticed some differences due to different versions of OpenCV, differences in speed. I don't think the differences were in accuracy. We did have issues with trying to use the same version of Eigen across ARM and Intel platforms, and having the applications running on the ARM platforms result in segfault or some other issues that were even harder to debug. So this is one choice that we've made, initially thinking only about a limited number of systems, but as the number of systems grows, it gets harder and harder to maintain a set of dependencies that works across the board. The other option, which I would, in hindsight, recommend, is to use separate containers. So sort of build perhaps Docker containers for each of the various systems with their own dependencies, accepting that the dependencies might introduce some changes. And I think just in terms of practicality, this ends up working a little bit better. Another issue also also related to dependencies is that very often systems have their own CMake files to try to pull in their library dependencies. If you try to have everything being built by the same build system, you can end up having conflicts between the CMake files. One last thing that I'd like to talk about is trying to automate ablation studies. So ablation studies are evaluation methods where you're trying to figure out how much each of the components of the system contributes to the final results. And so in the context of SLAM, and something that was already brought up is that certain features of SLAM and spatial AI systems are actually quite closely related. So as an example, 3D reconstruction is dependent upon the quality of pose estimation. And so this is not something that we've done yet. One of the references that I have at the end is a really nice paper published recently on looking at this. But essentially, what you'd like to do is both assess the quality of 3D reconstruction with the estimated pose by the system and the quality of the 3D reconstruction with ground truth poses. And the same goes for higher levels if we go to semantics and probably later on to interactions. I think I spent quite a lot of time, so we can talk about the dataset format if anyone is interested. But what I'd like to do is to move on to thank to all the contributors and collaborators we've had over the years. It's been quite a journey, and I'm really happy with the work that we've done so far, and I'm really looking forward to having a collaboration with ILLIXR as well. The research has been supported by Pamela and RainHub grants, and also the Royal Academy of Engineering ARM Research Chair. And we have a list of references relevant to the presentation. So thank you very much.
Yeah,
I'm happy to take questions.
Yeah, thank you so much. This was really great. I think you hit on a lot of issues that we have run into, and it will be just awesome to work together. And not just the core ILLIXR team so far, but the point of the consortium is to reach out to the entire community and get us all working together and creating infrastructures. These really complex infrastructures that we can all benefit from. So yeah, I'd like to open this up to questions. Josefa, I saw, did you raise your hand?
No, just, yeah.
I have some questions. I don't know how to raise the hand. But,
Yeah, okay. Yeah, go for it. Yeah.
Sure.
Yeah.
Okay. So I have so many questions, but I will try to keep to the main ones. So I'm working on Monado and trying to do something very similar to what you're doing. In particular, for having like at the level 1, just having a good tracking for XR devices.
Yeah.
And so we have done something kind of similar to what you've done, doing like an interface that different systems have to implement. We have implemented Chimera, Orphan 3, and Basalt. So we were discussing with ILLIXR it would be pretty cool to have like an standard interface, and Slumbench seems to be like a pretty nice quick start. I wasn't that aware of the project until recently, thanks mostly to this talk. So some question I have is regarding like how much are you focusing on real-time trajectories? The problem we are having for example, Orphan 3 is that Orphan 3 generates a very nice trajectory, but once the entire data set gets processed, when you use the partial trajectory it generates, it's not that good, and it usually because you have like the separate thread of which does the bundle adjustment, the mapper thread, which kind of like corrects and makes the trajectory jump a lot.
Yes.
So we are trying like to implement some metrics to evaluate that. Things like relative pose error help, but have you had some experience with that, with focusing on real-time usage?
Well, so I know what you're talking about, and it's a pain, is what I can say. What we're doing is when we report the final error is, you do a final realignment of everything with the final pose, and that's what you report. But in terms of what happens in real time when there's bundle adjustment, so one of the issues that we've fixed, and I'm not actually sure whether that's pushed to the main repository, is that initially we were just getting the latest pose output and just adding it into the poses we already had. So if you don't go back whenever things get corrected or loop closure happens, then you just get poses that are kind of jumping, but without having corrected the previous poses. So that is an issue. Are you asking this in terms of just kind of visually looking at how a system performs, or
Probably
in terms of...
on the metric side, like, have you considered some metrics to address this? Like, for example, Option 3 in paper is like very good, like in metrics, but
Yeah.
when you compare it to simpler solutions that just implement vision inertial autometry, in real time, like it's worse compared to that because of these issues. Like, like, yeah, mainly metrics. Like, do you have some metrics for that, or have you considered metrics for measuring that?
So I'm not entirely sure when you say, so what we do with Sunbench is that we feed all of the inputs in a data set and wait until the processing is reported as being done by the system. And so there isn't any, we try to make sure that there isn't any kind of frames being dropped or things being skipped, mainly because that helps with reproducibility. There is, of course, an argument to be made that it's important to also assess how well systems are doing when they do drop frames and do all the other things, but it's harder to ensure that it's being reproduced. You'd have to perhaps save up the frames that are being dropped, or have a way of consistently measuring this.
Okay.
So I mean, well, I think what you may be also alluding to, Matthias, that when you have real-time experiments, there's no ground truth typically, and so the metrics to figure out error don't have ground truth. It's hard to generate pose errors. I don't know if that's
also an issue.
If that's what you're alluding to.
Not necessarily, but that's another issue to have in mind when you are developing new real-time, new data sets that you take with new devices. That's true. Just to be quick, I will ask the next question so that I end. The next thing I noticed is the dependencies issue you put emphasis on,
Sure.
and we dealt with that a lot, in particular with Egan. Is quite that thing that if you don't use the exact same Egan version and all that is pretty painful.
Yes,
We're thinking
it's such a pain.
Yeah, and like all the dependencies depend on Egan, and all of them needs to be exactly aligned. So one of the ideas we had was to maybe implement some type of IPC, so just completely split the two processes. Have you looked a bit into that, or do you have any plans going into that direction?
No. So pretty much what I've been doing was bash my head on trying to find a version that works for the experiments that I'm trying to do at a certain time, and eventually decided that this is really suboptimal and we should switch the way we're doing to trying to have like separate containers or something. But it's an interesting and important, it's a really important issue. And I think there needs to be a larger discussion about how this should be dealt with. I'm sure there's hosts of researchers dealing with the same sort of problem.
Yeah.
Okay. Yeah. Thank you.
Josefa, do you want to say anything on this in this context?
No. I see Simon has his hand up. So
go ahead, Simon.
Hey, thank you. Thanks for the presentation. It was really informative. I'm from Berkeley doing architectural research, and when you talk about the robustness metrics, and you mentioned you evaluate different platforms such as desktop, laptop, and embedded. So I was wondering, have you observed anything like how the robustness metric changes across these compute platforms, and what are some of the insights you found that the compute platform plays into the robustness metrics of these algorithms?
So I think in our case, we found that things were fairly consistent with respect to robustness in terms of external perturbations. So in terms of what we've been discussing, what has been more of an issue has been what I've talked about with respect to dependencies. So finding that actually due to this particular dependency version not working on this particular platform, our results seem to be quite significantly different from what we're getting on another platform. The other point here is that, as I said, the way we deal with the systems is that we feed all the inputs without having any frames being dropped. So, you know, on the embedded platform in particular, we've had experiments that took very, very long, but we just let them run to make sure that all the frames are being processed. I think if we were to enable frame skipping or some sort of frame selection or dropping, then the results could be quite different depending on the compute resources that you have. But no, specifically with respect to robustness on the factors that we assessed, it seemed to be quite consistent.
I see. So you run this not in a real-time context, so you're not dropping frames,
No.
but the results are similar. Got it.
Yeah, exactly. But
That
you
makes
know,
sense.
especially when there's fast movement, possibly also with dynamic objects because the changes are significant. I would expect that in a real-time context, we would see something quite different.
Makes sense, yeah. Thanks a lot.
Thank you.
Hi, Mihai.
Hello.
It's Bujanca here. Thanks for the presentation. I have a question.
Yeah.
So I saw you evaluate RB-SLAM3 on your dataset with the STIR-MU, and I'm assuming you are testing RB-SLAM3 on other sequences using RGBD. Is that correct?
Yes. Yes.
So is there a particular reason that you didn't use STIR-MU on other sequence, on other datasets?
So we've chosen whichever sensors were supported by the dataset. So our RGBD, where we had only RGBD inputs, you know, sure, ideally it would have been good to standardize or compare this a little bit further. But yeah, so for instance, for the bond dynamic dataset or the Illumination dataset, there was no IMU and no stereo. It was just RGBD. Whereas for UROC, you have stereo, but there isn't any depth. Well, you have stereo IMU, but there isn't any depth. So here we've had to sort of adapt to what the dataset had available.
So do you have a rough idea that whether RGBD is going to be better or STIR-MU is going to be better on a data set with both, let's say, ETH3D?
So I haven't done the experiments, but just my feeling is that because we've done some comparisons with stereo versus stereo IMU, we haven't, even though we haven't done with RGBD and stereo IMU, my feeling is that stereo IMU would do better.
I see. Yeah, because recently I'm testing RB-SLAM3 on ETH3D, and one issue I found, I don't know if you've ever encountered this, is that when I run either monocular MU or STIR-MU, the algorithm works fine, and they detected the key points and the match the key points just looks like not that much bad, but suddenly it's just get total lost. And in the RGBD mode, when you lost of tracking, you can do the loop you can do relocalization later when you visit the same position or extract the same set of key points. So you do not lose the previous map, but in the stereo or monocular with IMU mode, the entire map just lost and the system seems like restarted. So I wonder
I
if
actually remember having a similar issue, which was again, I believe, dependent on the platform I was running it on. I think. So does just stereo work, but no stereo IMU? Have you tried just stereo without the IMU?
not yet. This is my next step.
Yeah. So do try that. I remember having some problems with this. Most of the time, the solution for us was finding. I think usually it was a problem with G2O and Eigen. I very vividly remember have sort of this this PTSD feeling of Eigen messing up certain certain things. And so yes, the first thing I would say is check the pure stereo mode and then have a look at how G2O is compiled.
Okay, so you believe that might be a G2O version issue?
It's possible, but you know.
Yeah, I can give it a try.
Sure.
Yeah, but the interesting thing is that even for some of the sequence that finished completely, I found that RGBD is actually better than stereo MU, which is not as I expected.
That isn't what I would expect either. I haven't tried that specific data set, but generally I've found that, yeah, pretty much everything that we've done with stereo IMU, it seemed to be really good. There were some really strange sequences where monocular IMU did better than stereo IMU. I haven't figured out exactly why that was the case, but generally I would, you know, if I were to pick something without having any additional information, I would say probably stereo IMU is the best. But I'll have a look.
I see. I see. Thank you so much. It's glad to know I'm not the only guy who faces this stereo MU issue.
Yes.
Thank you.
No problem.
Yeah. Well, we are like well over our time, so I'm okay to continue, but I don't know about Mihai.
Well, I'm happy to continue.
Okay.
Yes, sure.
All right. Do we have other questions from the audience?
I mean, I can go on and on.
Yeah, I know. Same here. So you know what? Maybe we should. Yeah, exactly. So maybe we should
let's stop the recording.
Huh? Okay, yeah, let's stop the recording. That's fine. All right. Well, thank you so much, Mihai. Before I stop the recording, this was really, really good, and yeah, really looking forward to you know, more work together.